Dubro Suspicion Files.
Okay, let's dive in. For decades, the moon has just sort of existed in our imagination as this romantic, singular goal, the ultimate symbol of what we can do.
The flags and footprints era.
Exactly.
Yeah.
But the sources you've shared with us, they reveal that the return to the moon is something entirely different now. It feels immediate, it's intense, and it really is the opening move in a new, very complex geopolitical contest.
That's right. We are no longer talking about a purely scientific or, exploratory return. What we're witnessing is the start of a genuine strategic and economic competition.
A lunar shadow war, as you put it.
I think that captures it perfectly. The stakes involve controlling what is arguably the most valuable, geographically constrained real estate in the entire solar system.
And at the center of that is the Artemis program. It's led by the U.S., of course, with international partners, and its explicit goal is establishing a sustainable human presence.
Right, a permanent base that can act as an indispensable stepping stone to Mars.
But again, the sources confirm that targeting the lunar South Pole isn't about just planting another flag. This is a highly calculated move, and it's rooted in a concept the sources keep hammering home: geographic determinism.
That phrase, just. It perfectly encapsulates the entire problem. The core of this conflict is defined entirely by the geography of one resource: water ice.
So you have the U.S.-led Artemis Accords coalition on one side,
Competing directly with the China-Russia International Lunar Research Station, or ILRS, on the other. And they're both racing for the exact same, very limited territory.
and the reason that territory is so vital boils down to needing two resources that are, by their very nature, completely at odds with each other, mutually exclusive.
You've hit the nail on the head. You can't survive without both, and they absolutely have to be neighbors.
So on the one hand, you need constant, persistent solar illumination for power.
That comes from the high ground, the elevated ridges the sources call the peaks of eternal light, or POELs.
And on the other hand, you need sequestered frozen water ice for life support, for consumables, for rocket propellant.
And that is found in the deep low ground, the permanently shadowed regions, or PSRs.
It's the ultimate cosmic real estate dilemma, isn't it? You have to build your base in what is basically the most blinding sunlight you can find for power.
But your industrial mining operation has to be able to access a well that's in the deepest, most crushing shade imaginable.
And that tension, that's what defines the entire game.
It does. That proximity requirement, the fact that you must have these two things side by side, inherently escalates the geopolitical friction over these very, very limited zones.
So our mission for this deep dive is to unpack every layer of this for you. We need to look at the strategic divergence, how Artemis is betting on solar power while the ILRS is going nuclear.
We also have to examine the high-stakes legal race for what's called first-mover advantage.
And crucially, we have to analyze the technical hurdles facing Artemis.
Yeah.
Those Government Accountability Office reports are, well, they're alarming, and they could jeopardize the U.S.'s lead entirely.
We need to understand not just what the moon has to offer, but how its unique hostile environment converts these potential resources into objects of intense strategic competition.
Okay, let's start with that fundamental geography. Why the poles? And more specifically, why has the South Pole become the absolute center of this new strategic universe?
It all comes down to what you could call the cold trap economy, and that is driven by these permanently shadowed regions, the PSRs.
For anyone less familiar, what exactly defines one of these zones?
So a PSR is basically a deep crater or a topographical low point, almost always near the moon's poles, that is in a state of near constant darkness.
And that's because of the moon's tilt, right?
Exactly. The moon's axial tilt is incredibly shallow, only about 1.5 degrees relative to its orbit around the sun. So because of that shallow angle, the sun is always on the horizon from the perspective of the poles. It never gets high enough in the sky to shine into the deepest parts of these craters.
And without that direct sunlight, they become cryogenic freezers, preserving conditions that are way more extreme than I think most people realize.
Yeah. Way more extreme. The sources indicate that temperatures inside these cold traps can drop below 110 Kelvin. That's about minus 163 degrees Celsius.
Okay, that's cold.
But we've mapped areas in the very deepest shadows that get even colder, down to minus 250 degrees Celsius or minus 418 Fahrenheit.
Wait, minus 250 Celsius. The sources put that in context, saying
It's genuinely colder than the average surface temperature of Pluto.
colder than Pluto in our own celestial backyard. That kind of stable, extreme cold must create some unique conditions for geology.
It does. It creates what's called the cold trapping mechanism. Any volatile molecule, and we're mostly talking about water here, that ends up in that darkness, whether it's from a comet impact or the solar wind, it's immediately flash frozen.
And it just stays there.
It's permanently sequestered. The temperatures are so low that sublimation, turning from a solid straight to a gas, is effectively impossible. So these volatiles have been preserved for potentially billions of years.
And this isn't just a theory anymore. The sources confirm there's decades of remote sensing evidence proving this water is there. What's the history of those discoveries?
It's a really fascinating bit of scientific detective work. It really started back in the late 90s with the Lunar Prospector mission. It had a neutron spectrometer that detected a spike in hydrogen near the poles, which is a strong proxy for water ice.
So that was the first big clue.
Right. Then you had the Clementine and Chandrayaan-1 missions, and they both used radar to look into these craters. They found these anomalous radar returns that were consistent with the presence of ice.
But the real game changer, the data that really made a program like Artemis even possible, that came from the Lunar Reconnaissance Orbiter, LRO.
Absolutely. LRO had a whole suite of instruments that gave us definitive proof. Its neutron detector, LENEND, gave us a much more refined map of where that hydrogen was.
And then there was a LAMP.
Crucially, yes, the Lyman Alpha Mapping Project, LAMP, measured UV albedo, basically how the surface reflects ultraviolet light, and the signature was entirely consistent with surface water ice. It was this comprehensive, multi-instrument confirmation that, yes, the volatiles are undeniably there.
And it's the sheer scale of this resource that makes it a geopolitical prize, not just a scientific curiosity. Give us the numbers the sources provided.
The current estimates, based on all that remote data, suggest that the lunar poles collectively hold over 600 billion kilograms of water ice.
600 billion, that's hard to visualize.
It is. So the sources give a comparison. That's potentially enough water to fill 240,000 standard Olympic-sized swimming pools. This is not a small deposit. It is an immense industrial-scale resource.
An ocean of potential rocket fuel just waiting to be harvested. But the LRO data also had some good news for mission planners about how easy it might be to get to, right?
Yes, a crucial finding from the Diviner instrument. While there is ice on the surface, the stability of that ice nearly doubles at a very shallow depth, just 2 centimeters, or about 0.8 inches below the surface.
So it's protected by a thin layer of dust, the regolith.
Exactly. It suggests that the subsurface ice is extensive and protected from even minor temperature swings, which makes it a really accessible primary target for the Artemis III mission.
So you don't necessarily have to drill down super deep to get to the good stuff, at least not at first.
And we should also emphasize that the story doesn't just end with water. The stability maps suggest other useful compounds like sulfur, carbon dioxide, even ammonia might also be trapped in these cryogenic freezers.
So if we can get those out too.
The South Pole becomes more than just a gas station. It becomes a critical source for long-term, multi-purpose industrial processes and life support.
Which just reinforces the need to control these specific areas. But, like we said at the top, resources in the dark are useless if you don't have power from the light. Which brings us to the other half of the equation. The peaks of eternal light. The POELs.
The POELs are what make any of this possible. Because of that same shallow axial tilt, you have these elevated spots crater rims, ridges, like those around Shackleton Crater, that receive near-constant solar illumination.
How constant are we talking? I mean, the lunar night lasts for 2 Earth weeks.
It's remarkably reliable, which is why they're so valuable. Analysis shows specific high points can stay lit for more than 80% of an entire lunar year.
Okay, that's impressive.
But more importantly, even at the lowest point of the lunar day, when the sun is mostly down for everyone else, these POELs still maintain a minimum illumination of between 44 and 64%.
So that's a guaranteed power you need to survive that 14-day night. It turns what should be a total blackout into more of a manageable power dip.
And that is where the strategic genius and the immediate friction comes from. The prime real estate is defined only by the strategic juxtaposition of these two features. You need a polyL right next to a PSR.
Your base needs to be in the light, running on solar panels, but your mining rovers need to be able to make short, efficient trips into the darkness to harvest the ice.
That mandatory geographic concentration is the engine of the whole geopolitical tension. It guarantees that the U.S. and the ILRS are competing for the exact same few square kilometers of lunar territory.
And if we compare the two poles, the sources say the South Pole has a clear advantage over the North Pole.
It does. It has a higher concentration of these really rich PSRs, and critically, a much higher potential for that near-permanent solar power, that greater than 80% annual fraction we just talked about.
So better resources and better power.
Correct. And we shouldn't forget the pure science benefits either. The South Pole gives you access to ancient, pristine geological samples, and because it's on the far side from Earth's perspective, it offers a radio-quiet environment that's perfect for next-generation astronomy. It's just superior in every metric.
Okay, so the resources are there, the location is perfect for power, and the conflict is literally defined by the map. That brings us to the next critical step. How do you actually turn that 600 billion kilograms of ice into a working, sustainable economy? In-Situ Resource Utilization, or ISRU, that's the core doctrine for Artemis. The whole idea is to stop relying on shipping everything from Earth, which is just catastrophically expensive.
Right, it's about living off the land.
So why is lunar water the single most strategically valuable consumable you can find up there?
It's all about its versatility and its chemistry. Once you extract and purify lunar water, H2O, you can split it through a process called electrolysis into breathable oxygen for life support and, critically, into high-energy rocket propellant.
Liquid hydrogen and liquid oxygen,
Yeah.
LOXLH2.
The most efficient chemical propellant we have. And a sustained presence means you're doing a lot of launches, right? You're moving cargo, you're moving crew. Every one of those launches requires tons of propellant.
Propellant that you absolutely cannot afford to ship from Earth. Every kilogram you launch costs tens of thousands of dollars.
Local production is the only way to make it permanent. The numbers show that just to get a return vehicle off the moon and back to the orbiting gateway or to Earth requires tons of propellant. ISRU turns an expensive one-way supply chain into a real internal economy.
But obviously, turning icy, minus 250-degree dirt into high-grade rocket fuel is not a simple process. The sources detail a really complex technical pathway. Let's walk through the steps.
Okay, so it starts with extraction. The main methods being looked at are what's called passive thermal mining. You need to turn the ice into a gas of vapor so you can capture it.
So you're basically just heating the ground.
Essentially, yeah. You can do that with concentrated sunlight from large mirrors or with electrical heating elements drilled into the ground. The sources also mention integrated microwave heating systems being developed, which could be much faster.
So you heat the regolith, the ice vaporizes, and you capture that vapor.
Exactly. That water vapor, along with other trace volatiles, is then captured by a cold trap, basically a very cold plate, and it condenses back into impure liquid water or ice.
But the real challenge starts right after that, doesn't it?
Yeah.
The purification step. This seems to be a huge technical hurdle.
It is the Achilles heel of the whole process. The next step is electrolysis, where you use high voltage to split the water molecule. Modern electrolyzers are incredibly sensitive to any kind of contaminant. They require water that is ultra-pure and deionized.
What kind of purity are we talking about here?
We are talking about a conductivity spec of greater than 10 megaohms centimeter. If you have any dissolved salts, any tiny particles, any conductive contaminants at all, the whole system will short out and fail.
So you can't just melt a bucket of dirty moon snow and expect it to work.
Not even close. This is where it gets really complex. The impure water you've collected has to go through a rigorous purification chain. It starts with freeze distillation to separate the water from other unwanted volatiles like CO2.
And then you have to deal with the dust.
Right. And lunar dust is the enemy of all mechanical systems. It's described as being like electrically charged, sharp volcanic glass. It gets everywhere. So after distillation, the water needs to go through incredibly fine submicronic filtration to eliminate every last particle.
And all of that, the heating, the electrolysis, the purification, that all takes a huge amount of energy, which brings us right back to why you need those peaks of eternal light.
It's why the entire ISRU facility is inherently sensitive, high maintenance, and incredibly energy intensive. It's why the non-negotiable requirement for continuous power drives the entire strategic choice of location.
Okay, so let's talk about the economic payoff. If you can pull all this off, how does it fundamentally change the economics of space travel? This is the idea of delta V leverage.
Delta V leverage is the core economic principle of cislunar space. Delta V is just the change in velocity you need to get from one orbit to another. Launching from Earth requires a massive amount of energy to escape our deep gravity well.
But launching from the moon back to, say, low Earth orbit
Requires only a delta V of about 6.2 kilometers per second. It's a fraction of the energy it takes to lift it out of Earth's atmosphere. You save the biggest cost of the entire trip right at the very beginning.
So by making propellant on the moon, you eliminate the single biggest mass and cost driver for any deep space mission.
Precisely. The moon instantly transforms from being a destination into an indispensable staging area and fuel depot for everything else we want to do in the solar system.
The lunar launch pad concept, it really changes the math for deep space journeys.
Absolutely. The success of this South Pole ISRU strategy directly accelerates the timeline and the feasibility of human missions to Mars. Those missions no longer have to carry all of their return fuel with them from Earth, which is a huge mass savings.
So NASA is basically priming the pump with Artemis.
Yes, they're trying to mature these systems and establish the operational precedents for what will hopefully become a commercial lunar propellant architecture. They're building a first rest stop on the interplanetary highway.
Okay, we've established the what and the how. Now let's pivot to the who. The competition, this Lunar Shadow War between the Artemis Coalition and the ILRS. What's the nature of this China-Russia alliance?
The ILRS is a very deliberate, formalized counterpoint to the Artemis program and the Accords. It's co-developed by the China National Space Administration and Roscosmos, and it strategically pools China's growing launch capability and capital with Russia's deep historical expertise in long-duration spaceflight and, very importantly, space-based nuclear technology.
They're positioning themselves as the non-Western alternative for anyone who wants to go to the moon.
That's the idea. And their timeline is uncomfortably close to Artemis, especially given the delays we're seeing.
How close are we talking?
Well, the ILRS roadmap is aggressive. It includes the Change 7 mission in 2026 and Change 8 in 2029. Both of those missions are specifically designed to scout and investigate infrastructure sites near the South Pole.
And they're doing their homework right now.
They are, and their stated goal is a permanent research and habitation capability. Critically, China is publicly targeting a crewed landing before 2030, which puts them in very close strategic proximity to the delayed Artemis III mission.
And the core divergence, the source of this zero-sum game, really comes down to a fundamental disagreement on energy, doesn't it?
It does. Artemis is tied to solar power, totally reliant on those POAs. The ILRS is committing to something completely different.
What's their plan?
They are planning to activate a powerful, industrial-scale 100-kilowatt nuclear power plant by 2035. This is the ultimate strategic hedge, and it fundamentally undermines the entire Artemis solar-dependent strategy.
100 kilowatts.
Yeah.
How does that translate into operational independence?
It gives the ILRS unparalleled freedom. They get continuous 2/4-73665 power. They completely bypass the single most crippling limitation of lunar development, that 14-day lunar night.
And they're not subtle about this being a strategic choice.
Not at all. It's explicitly framed as achieving zero reliance on Western tech. It is a direct and very potent critique of the vulnerability that comes with relying on intermittent solar energy, even at the best locations.
Because even if a pole gives you 80% illumination, that still means 20% of the year your base is running on batteries, scaling back ISRU operations.
Right. Nuclear power just laughs at that vulnerability. And this nuclear strategy is, at its heart, a long-term resource control maneuver.
What do you mean by that?
To get to the densest, most stable ice deposits, you have to drill into the deepest parts of the PSRs where the sun literally never shines. Running a deep thermal mining operation in permanent darkness requires a tremendous amount of reliable power.
And you can't just run a long extension cord from your solar-powered base on the ridge.
Exactly. The power loss would be immense, and batteries aren't going to last for a 14-day night of heavy industrial work. Nuclear power changes all of that.
So the ILRS can position itself as the only group that can efficiently mine the most valuable, most inaccessible deposits.
Potentially, yes. It could give them effective control over the deep resource economy, no matter who controls the sunlit ridges. It decouples resource accessibility from solar accessibility.
So this is about more than just who gets there first. It's a competition over the playbook, over the standards for how we develop space.
It's a standards war, absolutely. Artemis is trying to create this cooperative cislunar grid with its LunaNet standards. The idea is interoperable docking, shared power, common communication protocols among all its 55-plus partners.
But if the ILRS gets there first and sets up its own non-interoperable infrastructure.
That creates what the sources call a fragmentation risk. It's a critical risk for the future of space exploration. If you have two rival systems, any third-party nation or commercial company is forced to choose between them.
You have to pick a side.
You pick a side, and that drastically slows down the kind of cooperative logistics you need for bigger goals, like a unified human mission to Mars. It's just like historical conflicts where control over infrastructure like standardized railway gauges dictated economic access for decades.
And this entire strategic and technical race is happening in what is essentially a legal gray area, isn't it? The rules for who owns what are being written in real time through actions, not treaties.
That's right. International space law is fundamentally uncertain about resource extraction because the foundational document, the 1967 Outer Space Treaty, was written decades before any of this was technologically viable. The law is trying to catch up to the tech.
The OST, it clearly prohibits national appropriation of celestial bodies. That's the bedrock. But that phrase is, well, it's very ambiguous.
It is the central legal tension. The ambiguity is in defining appropriation. Does it ban sovereignty claims, like planting a flag and saying this land is mine? Yes, clearly.
But does it also ban ownership over the resources you extract? The water ice, for example.
Right. And that's the gray area. This lack of clarity, what legal scholars call non-licit, creates immense uncertainty for both countries and private industry.
So analysts are forced to look for analogies, right? Like deep seabed mining or Antarctica.
Which operate under the concept of the common heritage of mankind. The Artemis Accords are a direct attempt to bypass that messy legal history.
So what exactly are the Accords? What is their function?
They are a U.S.-led political agreement now with over 55 signatory nations. They are not meant to replace the Outer Space Treaty, but to clarify it and operationalize it in a way that carves out the legal space needed for commercial resource use.
And what's the single most important legal assertion the Accords make about ownership?
The Accords explicitly state that, and I'm quoting, "The extraction of space resources does not inherently constitute national appropriation under Article 2 of the Outer Space Treaty. That is the legal foundation for the entire commercial lunar economy."
So by saying extraction is not appropriation, the U.S. is providing the legal certainty that private companies need to invest billions of dollars.
Precisely. It's a direct strategic response to the failed 1979 Moon Treaty, which did contain those common heritage provisions and effectively scared off private investment for decades. The Accords are designed to attract it.
So the immediate goal for Artemis isn't just technical, it's legal. It's to define customary international law through action. This is the race for first mover advantage, or FMA.
Geopolitical strategists universally agree there's a potentially serious first-mover advantage here. The first actor to consistently conduct resource extraction, set up safety zones, and establish monitoring frameworks is the one who effectively defines the norms that will solidify into customary international law.
It's a race for normative hegemony.
It is. So the Artemis FMA strategy is twofold. Be the first to innovate and invest in ISRU, and be the first to employ those practices under the Accords framework.
And the stakes of delay are huge.
Enormous. If the ILRS moves first, their independent practices, established outside the Accords, could challenge the U.S.-led norms and set a rival precedent. You'd end up with a fractured, contested legal domain in space.
And the ILRS's nuclear plan complicates this legal picture even more.
It really does. It introduces a unique legal risk, because nuclear power gives them access to resources in these vast, deeply shadowed zones that are outside the sunlit areas Artemis is targeting.
So they could claim legal and operational precedent over non-overlapping territory?
That's the strategic point. They could achieve legal precedence over a much larger piece of the resource map simply by having better energy infrastructure. It makes future boundary and safety agreements exponentially more difficult if one side is operating sustainably where the other side can't even survive the night.
Okay, so the strategic need to get this first mover advantage is huge. And yet, our sources, especially those from the Government Accountability Office, the GAO, they reveal some major vulnerabilities in the Artemis program's health and its schedule.
The GAO has been absolutely unequivocal. Their assessment is that the Artemis schedule is, and this is their term, overly ambitious. They argue that this accelerated pace is actively increasing technical risk and, frankly, reducing the likelihood of success on the established timeline.
So compressing the time is eroding the strategy.
Exactly. And let's focus on the human landing system, the HLS. That's the cornerstone of Artemis III, the piece you need to actually land a crew and establish that FMA.
What's the timeline pressure on the HLS specifically?
Well, the program is trying to develop, build, and test this incredibly complex human-rated lander in just 79 months. The GAO points out that this is 13 months shorter than the average for NASA's other major projects, many of which are far less complex than this.
That kind of pressure cooker environment has to increase the risk of cutting corners.
And we are already seeing the fallout from that. As of late 2023, the HLS program had already delayed 8 of its 13 key milestones by at least 6 months. 2 of those have slipped entirely into 2025, which was the year the mission was originally supposed to launch.
So the current late 2027 target for the crewed landing is looking optimistic.
The GAO analysis suggests it's highly likely to be delayed further if things continue on this track.
And beyond the delays on individual parts, the sources point to a bigger structural flaw in how NASA is managing this: systems integration gaps.
This is a critical organizational problem. The Artemis program lacks a unified top-down systems integration plan for its 3 main elements: the SLS rocket, the Orion capsule, and the SpaceX HLS lander.
So instead of one authority making sure everything fits together.
Components that are managed by different NASA centers, Marshall, Kennedy, Johnson, are basically expected to self-integrate in a distributed way.
What does that mean in practice?
It means the responsibility for making all the dissimilar software and hardware talk to each other seamlessly is decentralized. Different centers have different coding standards, different risk tolerances. Relying on self-integration just magnifies the technical risks and makes software bugs and interface issues far more likely.
Now, we have to talk about the single biggest technical vulnerability, the sources detail, the one that poses an existential threat to the whole FMA goal.
You're talking about cryogenic propellant transfer. This is the high-risk, high-reward bet that the entire Artemis III mission architecture is built on. The SpaceX HLS lander, their Starship, it doesn't launch fully fueled from Earth.
Right. It relies on launching multiple tanker flights first,
Yeah.
maybe 10 or more.
To ferry cryogenic propellant to an orbital depot in Earth orbit, the lander then has to go up, rendezvous, dock, and successfully refuel before it can even head to the moon.
And what do NASA's own documents say about how mature that technology is?
Limited progress. The technologies for on-orbit cryogenic storage and transfer, especially with liquid hydrogen, which just wants to boil off, are still immature and largely untested at this scale in a real space environment.
So this dependency on a complex, unproven capability is a major strategic threat.
It is. Every single delay in mastering this technology is a direct erosion of that FMA window. It just gives the ILRS more time to implement their nuclear alternative, which, by the way, doesn't have this orbital refueling hurdle.
And that's not even mentioning the basic environmental risks like lunar dust.
Right, which we talked about. It's not just an irritant, it's electrically charged, it's highly abrasive, and it poses severe risks to crew health and to the equipment. It destroys seals, it gets into avionics.
Have the mitigation efforts caught up to the risk?
Officials are still deeply concerned. NASA is testing new cleaning techniques, but the cumulative dust exposure risk to the crew has not been fully mitigated. And on top of all that, Artemis III is trying to operate in PSRs where temperatures can swing by 60 Kelvin over very short distances.
So you have an unprecedented level of operational risk combined with a schedule risk, all to meet a politically defined timeline. Okay, so let's synthesize this whole strategic picture. The need to get to the South Pole, to establish the legal precedent of the Accords, it's undeniable. But that FMA window is closing fast because of these deep programmatic risks.
Especially the immaturity of that cryogenic refueling technology.
And the whole contest is defined by these two opposing energy philosophies: solar vulnerability versus nuclear independence. The technical risk is directly translating into strategic erosion.
It is. Which means the only path forward requires some immediate policy changes to mitigate these risks and, frankly, to decouple the political timeline from the harsh engineering reality.
So let's get into the recommendations. Policy recommendation 1, decouple FMA from the crewed landing.
Right. Relying on the high-risk, incredibly complex Artemis III human mission to establish first-mover advantage is just. It's strategically tenuous. If Artemis III slips again, we could lose the lead entirely. We can't put all our strategic eggs in the HLS basket.
So the recommendation is to shift high-tempo investment to robotic precursor missions, like the ones in the CLPS program.
This is critical. We should be tasking those CLPS missions to go out and execute definitive resource prospecting and even some basic localized resource extraction operations right now.
Before the crew gets there.
Yes. This establishes the technical and, crucially, the legal precedents, the FMA of the first to reveal and employ under the Accords framework before the inevitable crewed mission delays happen. It uses less costly, less time-sensitive means to establish legal facts on the ground.
You establish the rule of law robotically before you risk human lives to do it.
Exactly. Which brings us to policy recommendation 2, which deals with that big strategic hedge from the ILRS, accelerated nuclear research and deployment.
Their 100-kilowatt nuclear plan is a huge strategic advantage. We have to counter that.
NASA and its partners have to start treating the development of small-scale, space-ready fission power systems, like the successors to the 𝐃𝐿Power program, as a critical national security and geopolitical imperative. This can't be some long-term research project anymore. It has to be an accelerated deployment program.
And if we fail to deploy our own non-solar power solution,
we yield strategic control over all those deeply shadowed resources and long-duration operations entirely to the China-Russia coalition. The resource economy of the moon will be controlled by the party that can operate 247, regardless of the sun.
Finally, Policy Recommendation 3 addresses those organizational flaws the GAO found. Mandate a centralized systems integration authority.
The risk of mission-critical failure, especially with the complex software integration between SLS, Orion, and HLS, is just exponentially increased by this distributed management structure.
You need a single empowered authority that can force everyone to get on the same page.
Absolutely. This authority needs to enforce mandatory technical alignment across all the major segments. It needs specific mandates to resolve software issues and to develop standardized, crew-safe, lunar dust contamination protocols that apply to all the hardware. System-wide interoperability isn't a nice-to-have. It's the prerequisite for success and for establishing the LunaNet standards we want the rest of the world to adopt.
So this deep dive really reveals that the moon is no longer just a monument to past glory. It is a live-fire strategic contest for the control of cislunar space.
And that control is going to be dictated by who can manage the extreme technical complexity of ISRU and fundamentally who can achieve genuine energy independence, solar fragility versus nuclear autonomy.
The Artemis program has the legal framework with the Accords, but the ILRS holds a very compelling long-term strategic advantage with their commitment to nuclear power.
And that immediate race for FMA is currently being jeopardized not by a lack of vision, but by pure engineering complexity. Specifically, the challenge of perfecting on-orbit cryogenic refueling before the competition can leverage its own advantages.
What's fascinating here is that the immediate success of this whole ISRU strategy is directly linked to the long-term feasibility of ever sending humans to Mars. The moon becomes the economic engine for the entire solar system.
And that leads us to our final provocative thought for you, the listener, to mull over. The eventual boundary dispute over these lunar PSRs defined by solar accessibility on one side versus nuclear capability on the other is going to create two fundamentally different and potentially rival resource camps.
So how will that difference in operational scope and resource control impact the geopolitical cooperation we're going to need for the even larger unified goal of getting to the red planet? The moon, it seems, is the proving ground for the geopolitics of Mars.